Bioinformatics Micromodules. How difficult is sequence alignment? In this module, we'll discuss the difficulty of sequence alignment by analyzing the number of possible alignments given an input pair of sequences. First, let us use a simple example to recap some of the basic concepts in sequence alignment. Suppose we are given these two short sequences, ACG and AGG. In sequence alignment, we want to add gaps to these two sequences, such that in the final gap-filled sequences, the two sequences have the same length, and we cannot find any one single position with only gap characters in both sequences. For example, this is one valid alignment. In this case, if we consider a simple scoring scheme, in which we give a +1 score for a match and a -1 score for a mismatch or indel, the score for this alignment would be -2. This is another possible alignment. It involves one mismatch and two matches. The score is 1. One important question that we want to ask is, how can we find out all the alignments with the highest score? One obvious way to do that is to enumerate all possible alignments one by one. For each one, we compute the alignment score, and then after considering all alignments, we find out all those with the highest score. In order to know whether this is a feasible scheme or not, we need to know how many alignments are there. So in this case, the two sequences are quite short. We'll expect to have not too many alignments. But is that really the case? In order to systematically find out the number of all possible alignments, we can count the number of gaps that we want to add to the first sequence. If we do not want to add any gap to the first sequence, then correspondingly, for the second sequence, we should also not add any gap in order to balance the length of the two sequences. Therefore, there's only one valid alignment with no gap in the first sequence. If we want to insert one gap to the first sequence, there are 12 valid alignments. How can we find out this number 12? The way is like this. We want to insert a gap to the first sequence. There are 4 possible positions that we can insert this gap, namely before the A, between A and C, between C and G, and after G. Once we determine the position that we want to add the gap to the first sequence, we also need to add a gap to the second sequence. Now, there are only 3 possible positions that we can insert a gap, because we cannot insert a gap to the same position that we also insert a gap in the first sequence, which would make the alignment invalid. Therefore, for the 4 possible cases to insert a gap into the first sequence, each of them has 3 possibilities to add a gap to the second sequence. The total number of valid alignments is therefore 4 times 3, which is 12. Here, please notice that the first and the fourth alignments on the first row are considered different, even though they have the same way to align the characters in the two sequences. Later, we'll see that there are other possible definitions, but for now, let's use this simple definition. What if we want to add 2 gaps to the first sequence? We can do a similar analysis. After adding the gaps, altogether there are 5 positions in the first sequence. 2 of them are gaps. Therefore, the number of ways to insert the gaps is 5 choosing 2, which is 5 times 4 divided by 2, that means 10. For each of the 10 cases, again in the second sequence, we'll have 3 possible positions that we can insert gaps, and we want to add 2 of them. So the number of ways is 3 choosing 2, that means 3. Therefore, the total number of valid alignments is 10 times 3, which is 30. We can again do the similar analysis when we insert 3 gaps to the first sequence. And the analysis actually ends here, because we cannot add 4 gaps to the first sequence without having one single column with only gap characters in both sequences. So by summing up all these different cases, we find out that there are 63 possible alignments. Then we can compute the alignment score of each of them and compare. Finally, we find out that the one without introducing any gap has the highest alignment score. Now we see that even with these two short sequences, the number of possible alignments seems to be quite large. Now let's consider the general case in which the first sequence has length m and the second sequence has length n. The analysis basically goes in the same way. We want to introduce some gaps to the first sequence. The minimum number that we need to introduce is n minus m. And the maximum number of gaps without having any position having gaps only is n. Suppose we have decided to introduce x gaps to the first sequence. Then the total number of ways to insert these x gaps is x plus m choose x, because after adding the x gaps, the first sequence will have x plus m characters, among which we want to choose x of them to be gaps. Once we have this x fixed, correspondingly, we need to introduce x plus m minus n gaps to the second sequence. Again, these gaps has to be chosen at the places that we did not introduce a gap in the first sequence. So there are only m of them. Therefore, the number of ways we introduce the gaps to the second sequence is m choosing x plus m minus n. Now, x can take any value between the minimum and the maximum, so we sum over all these possibilities. After some simplification, we get this final formula. Let's plug in the numbers that we considered in the simple example before. M and n are both equal to 3 in that example. If we use this formula, we find out that the final number is 63, which is the same as what we got in the last slide. So in practice, how large is this number? Here we show a table considering the number of possible alignments for the two sequences having lengths from 1 to 10. You can see that when the two sequences both have length 10, the number of possible alignments is around 8 million. And this number actually increases very rapidly. So for any practical analysis with sequences longer than, for example, 20 or 30, it would be impossible to enumerate every one of them in order to find out the best alignment, even for a fast computer. As we discussed before, you may argue that we were using a definition of unique alignments, which is not too reasonable. There are other ways to define unique alignments. Here I'm giving you a reference so that you can see even in those cases, the number of possible alignments is still quite large. Since the number of possible alignments is so large, then how can we find out the best alignments? That would depend on how large m and n are. If they are not too large, say they are smaller than 10,000, we can use something called dynamic programming to efficiently enumerate all possibilities. The idea is that we do not really need to enumerate them one by one, because many alignments have shared parts. So once we have determined some partial results for one alignment, we can reuse that for other alignments. But even with dynamic programming, if m and n are very large, it is impossible to find out the best alignment. In that case, we are going to use something called heuristic. The term heuristic means that it is much faster, much more practical, but it does not guarantee to find out the best solution. So this is a trade-off between the performance and the optimality of the solution.